In this lecture, I'm going to discuss about a surface that is given by this equation, and its shape looks like a Tim Horton donut. And I want to discuss how we can represent this surface as a parametric equation, and then we want to find an equation that is normal to this surface. So this type of problem occurs in many applications, and we want to deal with complex surfaces, more complex than this what is shown here. So let's see how we are going to do that. And I want you think for a minute that how we can solve this problem. So we don't want to memorize any formula and see what we can do. Let's look at this equation. So the equation looks like this is something square plus something square equal to a constant square. So in that case, we might think of the trigonometry. So since on the right hand side b square, so on the left hand side we want b square times sin square theta plus cos square theta. So maybe we can write b square cos square, and instead of theta I'm just going to write the English letter v. So b square cos square v you can think of this way. It's obvious from trigonometric identity that b square cos square v plus b square sin square v equals b square. Simple. So what does it mean? It means that we have assumed here b cos v equal to the first term, and on the second term b sin v equals z. So we have something for z and something for x and y, but for x and y we have b cos v, but x and y are not directly written here. So we can perhaps think of a little more. So let's look at the first equation here. So instead of x square plus y square minus a, we can write a plus b cos b. And this tells me again, on the left hand side we can have another trig identity. For instance, the right hand side, let's denote it a constant number. That will be easy for understanding purpose. Okay, so x square plus y square square root of that equals r. So which means we can think of x equals r cos theta plus y equals r sin theta, right? So I'm going to use x equals r cos u and y equals r sin u. Okay, so now let's recollect what I have done. I can see that x equals, instead of r, a plus b cos v cos u y a plus b cos v times sin u, and z is b sin v. And we did not discuss any other knowledge about spherical coordinate system or cylindrical coordinate system or polar coordinate system, assuming that we can deal with that even if we have forgotten all those coordinate system. All we need to understand very simple mathematics like trigonometry, sin square theta plus cos square theta equals 1. That's all. And what we have done is that we have manipulated the given equation here. So this equation we have manipulated to get something here, and you see that we have introduced new variables u and v, and maybe we can now write that down in a slightly different form. So let's assume I have a vector function r which takes two parameters, and write in the vector form. Okay, so the surface has been converted into a new form, which is now a vector function of u and v. So this is a parametric representation of the given surface. Okay. So remember, the parametric representation is not unique, but it is very useful, and I like this type of process. Is one of my favorite technique when I do the computation and fluid flow modeling. You can basically take any surface and you can convert it in terms of a function of two parameters. So a surface generally in a three-dimensional space in Cartesian coordinate will be dependent on x, y, z, our usual x, y, z coordinate. You can convert that, make a substitution, and represent x coordinate as a function of two parameter, y coordinate is a function of two parameter, z coordinate is a function of two parameter, and that is just error trial, like regular substitution. Okay, so that's how you convert any surface into the parametric form. Once we have in the parametric form, now we have a coordinate transformation from x, y, z to uv. So now the surface is mapped into uv coordinate system, and in uv coordinate system I have the domain, and at every point from uv domain will be mapped to the three-dimensional surface. So basically we have somehow reduced the problem from 3-dimension to 2-dimension. And it is useful, like in 2-dimension now we can take the vector function r, we can differentiate, we can integrate. Let's see what happens if I differentiate. So let's take this vector function r, differentiate with respect to u, and very conveniently I can write that vector r sub u is the partial derivative of r with respect to u. And you know that when we do the partial derivative with respect to u of a multivariable, here the other variables, the v, we assume that the v is constant. So you look at here, you can very easily you can find the derivative. It's not a very complicated function. So differentiate each component. The first component, a plus b cos b is a constant. A plus b cos b will be treated as a constant because we are differentiating with respect to u. Derivative of cos u is negative sine u. So I can put the negative sign here. Second term, a plus b cos b times sine u, a plus b cos b, which is a constant with respect to u, and sine u becomes cos u. The third term we look at it is b times sine v, b times sine v, which is a constant with respect to u. We are differentiating with respect to u, so that will be 0. Okay. I'm going to tell you what does it mean with this derivative in a minute. But let's say we have differentiated with respect to u. Can we do a differentiation with respect to v? Yes, we can. So differentiate with respect to v. So this time cos u in the first term is a constant, sine u is a constant in the first term, and so on. So if I differentiate a plus b cos v, so that will be negative b sine v times cos u. So cos u does not change. Second term, the same thing, negative b sine v, and multiplied with sine u. And the third term, positive b cos b. Okay. So we have differentiated with respect to u, with respect to b. Maybe hypothetically, go back and look at the equation again. In the original form, it is a function of x, y, and z. Well, 3 variable. Maybe we don't care much about 3 variable, but now we want to differentiate it with respect to x. Imagine it is not a fun to differentiate. Well, we can. It is not difficult. You can differentiate 2 times this quantity to the power 1, and then use the chain rule and so on. Compared to that, if you look at here in the parametric representation, the differentiation is easier. Also, from a function of 3 variable in the parametric representation, it becomes a function of 2 variable. So you don't have to differentiate with the third variable. So your work is also reduced. Now, why I differentiated? What does it mean by R sub u? Maybe I draw a little bit of, see if we can visualize that the UV, right? And I don't know the shape of the surface. Maybe it stays very similar, or it may change. So let's assume this is what it is. So when I differentiate with respect to u, I assume b is fixed. So maybe somewhere b is fixed on this line. So b is fixed. So when b is fixed, that means you are on some cross section. So derivative of u, derivative of r with respect to u will give a tangent in y direction. Similarly, when you differentiate with respect to v, and then you keep u fixed, so that means you are looking at a certain point, and then you are looking for a tangent in v direction. So maybe we can just sketch it this way. So maybe you are in that point. So r sub u might be something like this, and r sub b might be something like that. You have to be careful. You have to look at very locally at this point, and at this point r sub u will be a tangent in y direction, r sub v will be a tangent in v direction, and you can do that at every point on the surface. And if you are dealing with this with a computer, then the computer does that's all you do is just you write the computer code, give the instruction, and then at every point you can loop over all points, and you can actually calculate those derivatives at any point. So that means once we have parameterized, we have calculated tangents at every point in u direction and in v direction. Now, what happens if you now take a cross product of Ru and Rv? So you know that cross product is orthogonal to to the original two vectors. So the cross product will be orthogonal to Ru, orthogonal to Rv at this point. So cross product because Ru and Rv is tangent on that local point. So cross product will be a normal. So which means we can easily now calculate normal vector on the donut. Let's call this a donut. At a point UB. So it will be, so let's denote it by n hat. Is that unit normal? But let's just denote it by n hat. So all we need to do is now calculate the cross product, and we know how to calculate the cross product. So let's recall ourselves. So in order to calculate the cross product, we need to form a matrix, and the first row of the matrix are just unit vectors in Cartesian coordinate. Well, so we have done a coordinate transformation, moved from Cartesian coordinate to the UV coordinate, but for doing cross product, we're just going to think of that, okay, because we have a mapping between UV coordinate to XYZ coordinate. So we will be still looking for the unit vectors in Cartesian coordinate. We don't have to do the unit vectors in the parametric form, in the parametric coordinate parameter space. Right? Yeah. So you look at here, R sub u, the first component, sorry, because b sin u. Second component is a plus b cos v cos u and 0. Now R sub b, the first component is negative b sin v cos u, negative b sin v sin u, and the third component is cos b. And now we take the determinant of the matrix. So actually we don't need to calculate the matrix, we just form the determinant, that should be enough. In principle, we form the matrix and then we calculate the determinant of the matrix. And this one will be just Cramer's rule, and maybe we can just write down in one shot. So once I have the Cramer's rule, I can get rid of ijk. I can use just the angle bracket and comma notation. So the first component will be, you look at this cofactor here, that will be a plus b cos v cos u. Let's put the v here, and cos v. okay, and minus 0. For the second component, for Cramer's rule, we get a minus sign. Let's just put a minus instead of minus 1. Okay, and then we calculate the cofactor. That will be this term times this term. Here is the minus sign. So the minus minus will be plus b times sine u cos b. Okay, and this minus this term times 0 is 0, so we don't need that. That term maybe I don't have enough room, so let's write down the here instead of this is not sufficient spot, so let's write down here. So we need this cofactor, so this times this minus this times that. So we have two minus signs, so that will be plus b times a plus b cos b. Sine u, and then sine v sine u, so sine square u sine v, again minus and again minus, which will be plus b times a plus b cos b cos u. Sine v cos u, so cos square u sine v, and this can be simplified further. I believe b times a plus b cos b can be taken out of the vector. Okay. Then in the first component will be cos u cos b. Second component will be sine u cos b. And the third component, you can see, if I take b times a plus b cos b out, I have sine square u sine v plus cos square u sine v, and you can take sine v out inside. You get sine v times sine square plus cos square, sine square u plus cos square u. So we need to have a little bit of practice in mental math, otherwise that indicates that we are learning. Instead of, we don't need to show all the works in detail. You see here sine square u plus cos square u. If you take sine v out, so I take sine v, and I'm thinking about that is because I know sine square u plus cos square u is our best friend in trigonometry, which is equal to 1. And this is my normal vector. So I can also find unit normal vector if I need it, or I can do something more later on. So before I finish this lecture, let's recap. What I have shown you is that you have a function. It does not have to be a donut shape. It could be a surface area of an airplane. It could be a surface area of Mount Everest, surface area of a mango, anything, any complex object. If we know the equation of the surface, we can make a coordinate transformation. So we are expecting that the given surface area in a three-dimensional space will be a three-dimensional function. We will make a coordinate transformation to convert it into a two-dimensional function, and this is called parameterization. So you express the three-dimensional surface as a vector of two scalar functions. So you see that there is a trade-off. You had a scalar function of 3 variables. Now you have a function of 2 variables, but you have a vector function, so you have to deal with 3 components. As I have already shown earlier, is that dealing with our original function in terms of differentiation and integration is relatively complex than dealing with your parametric function, and that is what is the objective of the parameterization, that you can make something easy. You can convert your problem into a relatively easy problem. When you choose the parameterization, this is a freehand choice. You have to look at, there is no unique way of doing that. There is no unique formula. So you have to use your intuition and then find a parametric representation. It does not matter which form you found, the final outcome will be the same. Once you have the parametric representation, what I have shown today is that you can differentiate with respect to each parameter. Then you form two vectors. Take the cross product, then you get the normal vector. Once we have the normal vector, we can do little more. In the next lecture, we'll come back and then we'll show how we can calculate surface area in this way. Thank you very much.